Hi, I'm Kyle. I'm in a group with Evan Blake and Frank Costa. They're behind the camera right now. For our project in fluid mechanics, we did the Magnus Effect. So the Magnus Effect, I have a quick diagram right here. Basically what we did, which is drop a ball, spin it, and it actually kind of floats. That's easily seen right here, where the airflow is going to the right. The ball has a backspin like this, going back towards me, and then that causes the airflow underneath to lift up with the ball due to the no slip condition, and it brings the force up, causing a lift force to cause the ball to float. All right, so the lift force. The lift force can be calculated by multiplying the lift coefficient by the frontal area of an object, multiplied by the density of the fluid, also multiplied by the translational velocity, and then squared, and then divided by 2. For this experiment, the same person was dropping the ball, each different object. So the translational velocity of each object was relatively the same, if not very close. So that can be neglected. The density of the fluid did not change because we dropped it at the same time of day, at the same place, so the density of the air was constant. The lift coefficients, although they were different shapes, you can assume that they were relatively close in numbers, so we neglected that. That leaves the lift force dependent on the frontal area. That's where we got our hypothesis of basically the greater lift force, or the greater effect of the Magnus effect, would be because of a larger frontal area of the object.
Hi, my name is Evan Blake. So for our project here, we had to make use of a place where we can drop a ball for a certain amount of feet. So the only place I can think of the best way was a fire tower. So we went to the Goat Peak Fire Tower. That's right near Mount Tom. So this is a 30-foot tall tower, but also where the balls would actually would land an extra 3 feet down. So think 33 feet of dropping. So how we actually did the project, so we had Kyle Diaz. Kyle Diaz dropped this ball every time. So just to cut out any other different things of different people dropping the ball, different forces, things like that. So we had the same person dropping the ball. I recorded every time, and Frank was collecting the balls down at the bottom. So how we ascertained where the actual start point of where the balls were actually starting, we pointed a laser pointer directly straight down at a 90-degree angle. And so from where that marking point was our starting point, and then we used a ruler to measure. So every time we would drop the ball, we did each object, we did 3 trials. And each of these trials, after we'd have dropped it, Kyle would go and put a marker down for where that ball landed initially. And then we would take a ruler to go from our initial point as indicated by the laser pointer to get our final distance. And like I mentioned before, we did 3 trials for each object, and they're all balls. And that is how we tabulated our data.
Hello, I'm Frank Costa. The first ball that we dropped was the soccer ball. The soccer ball has the second largest surface area. It is smooth, has sections with rough edges, which increases the friction. The second ball, the second object that was dropped was the paper towel. The paper towel, it has the 3rd largest surface area, and it was aided by plastic wrapping, in which greatly reduced air resistance and friction, which helped the paper towel travel farther. The toilet paper was the 3rd object that we dropped. The toilet paper worked as expected and finished. It was not wrapped, and it tumbled throughout the air since its flight path was not smooth. The 4th ball that we dropped was a football. The football finished with its expected surface area, and its lateral deflection of the ball of the flight was aided by its unique shape. The 5th object that we dropped was the basketball. The basketball has the 1st largest surface area due to the rough nature of the basketball. It has larger friction coefficient, thus shorter distance was traveled. And next we have the baseball and golf ball. They were both dropped. They both had the smallest amount of surface area and did not exceed well. Here we have just another different, more angles of the balls being released.
So as you just saw, in the videos we performed our experiment, we compiled all that data and put it into a data table. Frank basically explained how each of the balls or objects performed. The average distance that each traveled is on the right hand side, and in the first column we have the surface area. So the basketball, as you can see, it was first in surface area, but it traveled the third farthest distance, and the paper towel roll traveled the farthest. With this data, we made a graph to see if there's a trend between the distance traveled and the surface area, like we predicted in our hypothesis. And as you can see, although it's a very small sample size, as the distance traveled increased, well, as the surface area increased, the distance traveled also increased. Again, it's a very small sample size, but it's a basic trend, and we predict that for any object, it would also increase.